In this module, we explore the design capacity of compression members. We're going to look at what common compression elements are, the design capacity of the compression members, and in particular at buckling, because buckling does more often than not limit the strength limit state capacity of compression members. Compression members can be found in a lot more places than tension members. They're most common in trusses, but they can also be found in columns and studs in wall frames. So in a wall frame, a stud transmits wind loads through bending actions, but they also transmit the weight force of all of the elements that sit on top of the actual wall, and they do that in compression. The design equation. The design capacity has to exceed the strength limit state compression loads. The strength limit state compression loads are found by using loads that are factored by the strength limit state factors. And the behaviour of the timber member is going to be a function of its failure mode. There are two distinct failure modes, and this slide shows the pair of them. The first one is failure of stocky members, where the material actually crushes as the load is applied. If you look at that animation, you can see where the material is crushed, and you can see that the centre line of the member remains straight, so that the member has simply shortened as individual fibres in the member have crushed. The second mode of failure is more associated with slender members. And in this case, as the load is applied, you can see that the two ends are moving closer together, but that's accomplished and accompanied by the change of shape of the member. So you can see the yellow dotted line was the initial centre line, and now the member has moved away from that. That's a classic buckling failure, and that is the type of failure mode we tend to find with compression members. Here is the capacity of compression members. So again, you will see a phi, K1, K4 and K6. We've met these before for bending members and for tension members, and they're still part of this expression. You can see a K12 factor there, and the K12 factor models buckling just as it did for bending members. However, for compression members, buckling is different to the buckling of bending members, and the K12 value is evaluated slightly differently. And then at the end you can see a compressive strength times a compressive area. So stability. Stability is all about buckling, and the Euler buckling formula is shown on the slide, and you can see that the critical capacity, the Euler capacity of a column, is inversely proportional to the length of the column. The longer the column is, the more likely it is to buckle and the lower the load it can carry. So slenderness is related to the length of the member that has the potential to buckle. The stability factor then has to reflect the slenderness of the member. And you can see in these expressions, which are identical to the ones for the bending members, that if we have a stocky member, the slenderness times its material constant is going to be less than 10, and our K12 factor is 1. On the other hand, if we have a very slender member, it is a function of the slenderness squared. So that the higher the slenderness, the lower the K12 factor, and hence the lower the capacity of the member. The material constant is similar to a bending member, a function of the inelastic behaviour of timber. It does creep under load, and so if we have some deflected shape of the member and the load is maintained for a long period of time, it's going to tend to creep under that deflected shape, and the buckling is going to be accentuated. Likewise, it also reflects initial straightness of the member, and members with higher initial curvature are likely to be more prone to buckling. It does just allow for the realities of timber elements. The most important element, though, in the calculation of the K12 factor is the slenderness of the compression member. And there is a video that outlines the buckling modes of compression members, but for this one here, it's buckling in its minor axis. And the minor axis slenderness you can see on this slide is shown on the right-hand side as the length of the member divided by the breadth of the member, the thinner dimension, cross-sectional dimension of the member. Now, there's a slight modification. If the member has a lateral restraint, it's the distance between the loading point and the lateral restraint that is going to be the buckling length of the member. On the other hand, if there are no lateral restraints, a lot depends on how rigid the connections at the end are. If the connections are pinned, that is the buckled shape of the member. If the member is rigidly clamped at each end, we can actually induce some reverse curvature near the top of the member like that because of that rigid clamping. The G13 factor recognises that the rigidity of the connection at the end may affect its buckling strength. So where there's no internal support or intermediate support, there's a G13 factor that is incorporated into the evaluation of the slenderness. We evaluate the slenderness for the minor axis buckling. We evaluate the slenderness for major axis buckling separately. They use very similar formulae, as you can see on this slide. However, for major axis, the slenderness relates to the larger cross-sectional dimension, and for minor axis, the slenderness relates to the smaller cross-sectional dimension. We evaluate them both separately, and whichever slenderness is the larger one is the one that we use in evaluating the K12 factor. The last things to evaluate are the compressive strength of the material. And the compressive strength of the material can be found in the places that we are used to finding strengths now of the timber elements. So for sawn timber, we're going to look in Appendix H, for glulam in Chapter 7, for LVL in manufacturer's data. And that will give us the compression capacity. The compression area. The area over which the compression failure is deemed to take place is a function of holes in the member. If we have a hole in the member and there is a bolt in that hole, then as compression is applied to the member, the compression can actually pass through the bolt shank. So if there's a bolt in the hole, it doesn't interfere with the compressive strength of the member at all because the compression can simply pass straight through the bolt shank back into the timber. So we don't take account of holes that have got bolts in them. It's only if there's a hole that has nothing in it, so an empty hole, that we would take account of a hole in evaluating the compression area. So the compression capacity, 5 factor times K1, 4, 6, K12, which is the buckling factor for compression members, F prime C, the compression strength, and the compression area, which is the gross area minus any unfilled holes. Finally, with serviceability. Again, elastic serviceability can be calculated. If we have long-term loads, we take account of those long-term loads by using the J2 factor. But again, the shortening of a compression element is very, very small. And so it's rare that the serviceability limit state governs the design of compression elements. In this photograph, you can see a large number of compression elements. You can see vertical columns, so that those vertical columns would all have their capacities evaluated that way. You can see some major trusses that are running from the back of the photo to the front of the photo. Those trusses incorporate both tension and compression timber elements, and the compression elements would be evaluated exactly the same way as we have just been outlining. And finally, you can see some inclined trusses where the only timber elements are compression elements, and all of the tension elements are steel rods. So again, in the design of those compression elements, we would use exactly the same expression that we have been covering in this module. So in summary, compression members are commonly used in trusses, in columns, in studs. They're usually designed for the strength limit state, and we can check them for the serviceability limit state, but it's rare that the serviceability limit state governs the design. Buckling capacity is really important, and the buckling capacity is related to the slenderness, which is dictated by the length of the compression member, and in particular the distance between the lateral restraints of the compression member. The material constant we use to evaluate K12 is different for the compression member to the bending member. Row C is different to row B. And finally, the compression area is the gross cross-sectional area minus the area of unfilled holes.